Every time you've seen a great white shark, on screen, in a museum, in a documentary, you've probably been told the same story, that it's the closest living thing to Megalodon, a scaled-down descendant, the modern ocean's version of an ancient terror. That story is wrong, and it has been wrong since 1843, when a Swiss naturalist named Louis Agassiz placed Megalodon in the same genus as the living great white, based almost entirely on the shape of its teeth. Walk into any natural history museum with a Megalodon exhibit, and the label will almost certainly confirm the narrative. The two animals are displayed as part of the same lineage, ancient blueprint, modern copy. The great white is described as Megalodon's closest living relative, its diminished heir, carrying the same essential biology forward through time. In schoolbooks, documentaries, and museum halls on 4 continents, you'll find some version of this claim, repeated so often it stopped feeling like a hypothesis and started feeling like a fact. The scientific literature quietly corrected it, reaching a decisive point around 2019, when researchers formally placed Megalodon in an extinct family called the Otodontidae, completely separate from the family the great white belongs to. The two animals aren't ancestor and descendant. Their lineages diverged so far back in shark evolutionary history that calling Megalodon the great white's forerunner is roughly like calling a dog a smaller version of a cat. Both descend from a distant common ancestor, but they belong to different families, built on different biological terms, shaped by entirely different pressures. The comparison tells you almost nothing useful about either animal. The error that produced this misconception didn't begin with carelessness. It began with one of the best scientists of the 19th century doing exactly what the evidence permitted. But before Agassiz, there was Steno. In October 1666, fishermen working the waters near Livorno on the Tuscan coast brought in a very large shark. The Grand Duke of Tuscany, Ferdinando II de' Medici, ordered the head cut off and sent to a Danish anatomist named Niels Stensen, known by his Latin name, Nicholas Steno, who was working in Florence at the time. Steno was 28 years old and already one of the most rigorous anatomists in Europe. When the head arrived, he set to work dissecting it, splitting muscle from cartilage, mapping the jaw architecture, examining the teeth row by row. The teeth were triangular, serrated along both edges, dense, polished enameloid on the crown surface, rougher root material below. Steno had seen similar objects before. Everyone had. Throughout the Mediterranean world, triangular serrated stones turned up embedded in cliff faces and coastal rock formations. For centuries they had been called glossopetrae, tongue stones, and folk tradition had assigned them various origins. Petrified serpent tongues, remnants of the snakes that Paul the Apostle had turned to stone during his shipwreck on Malta. Objects with supposed anti-venom properties that medieval nobility fashioned into amulets and incorporated into tableware. When you burned a glossopetra, you got carbon residue. Fabio Colonna had noticed that in 1616 and used it to argue an organic origin, but the argument hadn't gained traction. Steno's version was different. He had a fresh shark's head on his table in Florence, and he had the glossopetrae, and the comparison was unmistakable. The same geometry, the same serration pattern, the same root morphology. He published his observations in 1667 in a work called Canis Carcariae Dissectum Caput, the dissected head of a dog shark. The tongue stones, he argued, were shark teeth, not mineral formations, not petrified tongues. Organic structures, once belonging to living animals, now preserved in rock. 2 years later, in the Prodromus of 1669, he elaborated the logic into a principle. Fossils were solids naturally contained within solids, material traces of once living organisms readable as identity records. A preserved tooth could tell you what animal grew it, where it had lived, and what the sediment around it implied about the sea that once covered that ground. In that single intellectual move, Steno established the foundation of paleontological reasoning. A tooth is a document. He was correct. That principle has guided fossil interpretation ever since. The problem, which wouldn't become apparent for another 168 years, is that two completely unrelated animals can independently evolve teeth that look nearly identical. Steno's method was sound. It would be applied correctly to the wrong comparative specimen. Louis Agassiz was born in 1807 in Moutier, in what is now Switzerland. By his late 20s, he was already a significant figure in European natural history, his reputation built on meticulous anatomical observation and an extraordinary capacity for systematic synthesis. He published Recherches sur les poissons fossiles, research on fossil fish, in installments out of Neuchâtel across a decade, from 1833 to 1843. The work eventually ran across multiple volumes and covered hundreds of species. It was, by any measure, a landmark document, the most comprehensive systematic survey of fossil fish then attempted, organized by families and genera, illustrated with detailed plates, and informed by access to collections across Europe. Picture Agassiz in 1835, in his study in Neuchâtel, working through the plates for the third volume's atlas. On his desk, or spread across a large table, as was common in comparative anatomy work of the period, are drawings of large fossil teeth. The specimens themselves are likely stone casts or actual fossils loaned from collectors. They are large, some over 100 millimeters in crown height, with robust triangular profiles and even fine serrations running the full length of each cutting edge. The crown surface is polished. The root is V-shaped, dense, marked by a dark chevron at the junction between enameloid and root material. In the fifth installment of the Recherche, the Atlas to Volume 3, Plate 29, Agassiz illustrated these teeth and named the species Carcharius megalodon, placing it initially in the genus of sand tiger sharks. The name itself means big tooth, from the Greek megalos and odon. The species became taxonomically valid at this point. By 1843, when the text volume of the same work finally appeared, he had moved the species to a different genus. Agassiz reassigned it to Carcharodon, the genus of the modern great white shark, yielding Carcharodon megalodon. His reasoning: the teeth were far too large for the sand tiger genus, and their serrated, triangular crowns aligned more closely with those of the great white. That reasoning was defensible from what he had. Great white teeth are also triangular, also serrated, also robust. In the absence of quantitative morphometrics, without tools to measure serration density precisely, to characterize root architecture numerically, to compare crown proportions statistically, the similarity was real and compelling. What we now identify as convergent evolution looked, through the optical instruments available in the 1840s, like family resemblance. Later analysis would characterize his decision as based on superficial morphological similarities in tooth shape and the presence of serrations. He had teeth, almost nothing else. This is the foundational structural reality of shark paleontology. Sharks have cartilaginous skeletons, not bone. Cartilage is mineralized in tiny calcified prisms held together by an organic collagen matrix. After death, when the collagen decomposes, the skeleton loses structural integrity and disperses into sediment, leaving no readable shape. The result is that almost no shark, across geological time, leaves a recognizable body in the fossil record. Devonian sharks are known primarily from teeth and scales. Cretaceous sharks are known from teeth and occasional fragments. Megalodon, which lived from roughly 23 million to 3.5 million years ago, is known almost entirely from the same evidence. What does preserve, readily, abundantly across geological time, is the tooth. Shark teeth are composed of fluorapatite enameloid, highly mineralized and structurally resistant to decay. A single large shark produces teeth continuously across its lifetime, replacing each one roughly every 1 to 2 weeks, shedding them into the sediment below. As Tyler Greenfield's 2022 catalogue of otodontid skeletal material notes, Their abundance in the fossil record is due to their enameloid hardness and high rate of production, which lead to a greater chance of fossilization. A single megalodon individual, over an estimated lifespan of 80 to 100 years, could have produced somewhere between 34 and 38,000 teeth. The Natural History Museum in London states the situation plainly. Almost all fossil remains of megalodon are teeth. The Belgian specimen catalogued as IRS-NB P9893, approximately 141 vertebral centra excavated from the Antwerp Basin in Belgium, is scientifically celebrated precisely because substantial skeletal material from megalodon is so exceptional. A partial vertebral column found in the Gram Formation of Denmark in 1978, comprising around 20 vertebrae including one centrum 23 centimeters in diameter, the largest megalodon vertebra ever recovered, was subsequently mislaid by museum staff, with only fragments eventually salvaged. The rarity of these specimens is the point. When Agassiz classified megalodon in 1843, no vertebral material was available to him at all. His type series was teeth, illustrated on a plate. You can't correct a body plan assumption from teeth alone, and when almost nothing else exists, the assumption stands. Agassiz's authority cemented the placement. His reputation on both sides of the Atlantic, he later became a professor at Harvard, one of the most prominent naturalists in North America, meant that Carcharodon megalodon became the operating name in the scientific literature and stayed there. Researchers who came after him worked within the genus assignment as a given. Every paper, every museum label, every popular account inherited the Carcharodon designation. And that designation carried an implicit argument. If megalodon and the great white share a genus, they share an evolutionary story. That implication drove everything downstream. For the next century and a half, the name Carcharodon megalodon served as the anchor around which every reconstruction orbited. Museums displayed megalodon teeth alongside great white jaws, framing the comparison as one of degree rather than kind. Documentaries described the great white as megalodon's closest living relative, its modern echo. The ancestor-descendant narrative, that today's apex predator is simply a smaller, contemporary expression of the ancient one, became so embedded in popular science that questioning it seemed almost pedantic. Then, in 1996, 3 researchers formalized the assumption into a physical shape that millions of people would stand in front of, look up at, and photograph. Michael D. Gottfried, Leonard J.V. Campagno, and S. Curtis Bowman published a chapter called Size and Skeletal Anatomy of the Giant Megatooth Shark, Carcharodon megalodon, as part of a volume titled Great White Sharks, The Biology of Carcharodon carcharius, published by Academic Press. The chapter produced the first widely cited, quantitative, full skeleton reconstruction tied to a published methodology. To estimate total length, Gottfried and colleagues developed a linear regression between great white shark body length and the height of the largest upper anterior tooth, a formula that yielded, for a tooth of 168 millimeters in crown height, a total length estimate of 15.9 meters. For skeletal proportions, they calibrated on vertebral dimensions measured from 16 extant great white sharks ranging from 1.9 to 3.7 meters in length, then scaled up. The resulting animal had a broad, stocky silhouette. A great white at roughly 3 times the scale, blunter cranium, wider jaws, thickened anterior mass, fins that followed the great white template because there was no other template available. The Calvert Marine Museum in Maryland installed the reconstruction. The Iziko South African Museum in Cape Town installed another. When the Calvert Marine Museum later commented publicly on their megalodon exhibit, they described the methodology exactly. Created by scaling up the size of a great white shark. This wasn't negligence. Campagno, one of the foremost living systematists of sharks, was well aware of the inferential nature of the exercise. The chapter explicitly acknowledged that extrapolations from the great white were necessary given the available evidence, and it critiqued earlier, cruder tooth height scaling methods by proposing more rigorous regressions as improvements. But the image that resulted, the barrel-shaped, immediately recognizable giant, became the canonical megalodon. Textbooks reproduced it, documentaries animated it, film productions borrowed its proportions. Every subsequent reconstruction that entered popular consciousness descended from the same 1996 template, which had itself been built directly on Agassiz's 1843 genus assignment. The abstract taxonomy of a mid-century text volume had become a three-dimensional object you could walk around in a museum hall. The first evidence that something was structurally wrong with this picture came from the same source that created the original classification: the teeth. Megalodon teeth and great white teeth, laid side by side on a lightbox or a specimen table, look superficially similar. Both are triangular, both are serrated, both are large relative to other sharks. For a long time that was the argument, and it was genuinely persuasive before anyone measured carefully. But examine the morphology with precision, and the differences are consistent, systematic, and impossible to explain away as individual variation. Megalodon teeth are thicker, measurably denser in cross-section than great white teeth of comparable crown height. Their serrations are finer and more regular, more numerous per millimeter along the cutting edge. They carry a distinctive chevron-shaped feature on the lingual face, the inner surface, called the bourlette, or dental band, a darker region marking the junction between crown and root. In megalodon teeth, this feature is prominent and clearly defined. In great white teeth, it's weak, inconspicuous, often absent entirely. The root structure diverges further. Megalodon roots are V or U-shaped, with a robust, projecting lingual protuberance. Great white upper anterior roots are comparatively rectangular, lacking the strongly developed root lobes that characterize the otodontid family. These aren't subtle gradations shading into one another. They're repeatable characters appearing consistently across the fossil record, pointing in different taxonomic directions. The University of Kentucky's Geological Survey describes the bourlette on megalodon teeth as a chevron-shaped feature called the bourlette, or dental band, clearly visible on the lingual side, distinguishing megalodon teeth from those of the great white, even to amateur collectors. FossilGuy.com's comparative overview, drawing on the published literature, is straightforward. Megalodon teeth are thicker, with finer serrations, a larger root, and a distinct bourlette at the base of the crown, while great white teeth are thinner, lack a bourlette, and typically show coarser serrations with a more slender root structure. In 2006, Kevin Nyberg, Charles Champaglio, and Gregory Ray published a geometric morphometric analysis specifically designed to test the ancestry question. They measured tooth shape variables quantitatively across multiple fossil shark species and ran multivariate analyses on the resulting data. Their finding: great white teeth cluster morphometrically with the broad-toothed mako, Isurus hastalis, not with megalodon. The two lineages occupied distinct, separable regions of morphological space. The University of Miami Shark Research Center, summarizing this research directly, concluded that Carcharodon carcharius originated from an extinct group of mako sharks and not from the megatoothed sharks. The similarities between megalodon and great white teeth weren't evidence of close relationship. They were evidence of convergent evolution. Two animals from entirely separate lineages, hunting broadly similar prey in similar oceanic environments, independently arriving at comparable tooth geometry through different developmental pathways and different evolutionary pressures. Convergent evolution means resemblance without ancestry. Dolphins and sharks look alike because the ocean rewards a particular hydrodynamic profile, regardless of which lineage produces it. The same principle applies here. The ocean also rewards a large, triangularly crowned, serrated tooth in any predator targeting substantial prey, and megalodon and the great white both needed that tool. The fact that both lineages built one tells you something about the ocean they shared. It tells you nothing about whether they were related. Megalodon belongs to the Otodontidae. The great white belongs to the Lamnidae. These are two separate families within the order Lamniformes, the mackerel sharks, and neither descended from the other. If that distinction sounds like a minor housekeeping detail, the relationship between these two families makes its significance concrete. Megalodon and the great white are as closely related as a dog and a cat. Both are mammals. Both descend from ancestral carnivore stock somewhere in the deep Eocene. But dogs are canidae and cats are felidae. Separate families, separate evolutionary histories, separate biological blueprints for predation. The comparison between them illuminates almost nothing about either animal's actual biology. The same is true here. Megalodon and the great white are both lamniforms, both descended from ancestral mackerel shark stock somewhere in the distant past. But they belong to separate families that built separate solutions to the problem of being a large marine predator. Their shared order-level classification tells you roughly as much as the fact that dogs and cats are both mammals. The Otodontidae are entirely extinct. Every species in the family exists only in the fossil record, and the family's range is substantial. Origins in the early Cretaceous, around 100 million years ago, running as a lineage through nearly the entirety of the Cenozoic era before the last member disappeared. The genera include Cretalamna, present in late Cretaceous seas and considered among the earliest relatives of the megatooth lineage. Megalolamna, known from the early Miocene and pivotal in the 2016 reclassification argument. Paratodus, Cenolamna, and the megatooth lineage itself within the genus Otodus, running from Otodus obliquus in the Paleocene through Otodus angustidens, Otodus tubutensis, and finally Otodus megalodon at the Pliocene terminus. The family's last species was Megalodon. After its extinction at the early to late Pliocene boundary around 3.5 to 2.5 million years ago, the Otodontidae closed. No continuations, no surviving descendants. The branch simply stopped. The Lamnidae tell a different story. 5 living species persist: the great white shark, the short-fin mako, the long-fin mako, the paw beagle, and the salmon shark. These animals share biological traits that define the family and explain its endurance. Regional endothermy, the capacity to maintain body temperature above the surrounding water, is achieved through a specialized heat exchange circulatory structure called the rete mirabile, a network of fine blood vessels that allows metabolic heat generated in working muscles to recirculate rather than dissipating into cold seawater. Lamnid sharks can sustain elevated muscle temperatures across a range of ocean conditions. Short-fin makos are among the fastest fish in the ocean. Great whites are capable of burst speeds that an animal optimized primarily for scale, as the otodontids were, likely couldn't sustain. The Lamnidae built their success on agility, metabolic flexibility, and a predatory range that didn't depend on the continuous availability of enormous prey in warm, shallow coastal seas. The great white's actual ancestry traces not to Megalodon, but to the extinct broad-toothed mako, Issurus hastalis, a lamnid already present in Miocene seas. A well-preserved Carcharodon specimen from the early Pliocene of Peru, documented in detail by Dana Ehret and colleagues at the University of Florida, revealed the transition in dental morphology. The fully serrated triangular teeth of the modern great white emerging from the morphometrically similar but unserrated or lightly serrated teeth of the hastalis lineage. The lamnid line was continuous and internally coherent. It had nothing to do with the otodontid line. They were parallel tracks, running through the same ocean for tens of millions of years without merging. The popular framing, great whites as mini megalodons, scaled down by extinction and time, isn't approximately right. It isn't right at all. The reclassification of Megalodon out of Carcharodon and into Otodontidae wasn't a single event handed down in a particular year. It was a gradual erosion of the old consensus, accelerating through the 2000s and 2010s as the morphometric evidence from Nyberg and colleagues accumulated, and as new systematic work clarified the broader architecture of the lamniform family tree. The 2016 description of Megalolamna paradoxodon was a turning point. Kenshu Shimada at DePaul University and colleagues announced a new otodontid genus from the early Miocene, a shark previously unknown to science that occupied a position within the family tree that created a problem. The genus Otodus, as then defined, was paraphyletic. It didn't include all of its own descendants. Making it properly monophyletic, ensuring that a genus includes all species descended from its founding ancestor, required folding in the megatooth species formerly assigned to the separate genus Carcharocles. That meant Megalodon belonged inside Otodus, within Otodontidae, not inside Carcharodon within Lamnidae. By 2019, that shift was visible across the specialist literature simultaneously. Bosenecker, Ehret, Long, Churchill, Martin, and Sarah Bosenecker published a major study in Peer J on Megalodon's extinction from the eastern North Pacific, treating the species throughout as Otodus megalodon and describing it explicitly as the last member of the predatory megatoothed lineage, a lineage distinct from the great white's ancestry. Shimada's concurrent size work used the same designation and family placement consistently. The name Carcharodon megalodon, which had linked the animal to the great white's genus for more than 175 years since Agassiz's 1843 text volume, no longer reflected where the specialist literature had arrived. Researchers now place Megalodon in Otodus megalodon within the extinct Otodontidae. A minority of authors still retain Carcharocles megalodon at the genus level. The debate at that rank is ongoing, but the family-level separation from Lamnidae isn't seriously contested in the current literature. The great white isn't in Otodontidae. Megalodon isn't in Lamnidae. Their common ancestor lies somewhere in the deep history of lamniforms, far enough back that neither animal offers a meaningful biological window into the other. Almost no one outside specialist paleontology noticed when the literature moved. The correction matters for more than nomenclature. Once Megalodon is removed from the great white's shadow, several assumptions built on the false taxonomy need to be revised, and the most immediate is the one that millions of museum visitors have walked past and accepted. The 1996 Gottfried reconstruction used great white proportions as the template for Megalodon's shape. Cooper and Colley's 2020 body dimension paper in Scientific Reports and their 2022 three-dimensional model published in Science Advances both did the same. The 2022 model used three-dimensional scans of living great white sharks as the base for Megalodon's body outline. All of these researchers acknowledge the methodological choice and its limitations. They were constrained by the available evidence and by the historical assumption that the great white was the closest living analogue. If you believe Megalodon was essentially a giant great white, you reconstruct it as a giant great white. The assumption feeds the image. Remove that assumption and the body changes. In 2025, Stearns, Shimada, and colleagues published a reassessment in Paleontologia Electronica comparing the neurocranial and caudal fin proportions of Megalodon's known vertebral specimens against 165 species of extant and extinct Neoselacian sharks across 10 orders. Their conclusion? A stout body plan like the great whites would have incurred excessive hydrodynamic costs for an animal of Megalodon's scale. The physics of drag at that size favored a slenderer, more elongated profile. Their maximum length estimate came to approximately 24.3 meters, longer than widely cited earlier figures because a leaner body requires greater length to achieve equivalent mass estimates. A 24-meter animal on those proportions would have weighed around 94 tons. The 2025 paper notes something telling. The vertebral evidence from the Belgian specimen and the Danish Gram Formation vertebrae, the largest yet found at 23 centimeters in diameter, had always been available. What changed was the analytical framework. When you stop assuming great white proportions, the same fossil evidence points in a different direction. That leaner reconstruction is, for most observers, stranger and more unsettling than the barrel-shaped version. A stocky great white, but bigger, is legible in familiar terms. You can almost imagine how it hunts, how it turns, where it fits in the visual vocabulary of shark cinema. Something longer and more streamlined, built along different biological lines, is harder to place. The reference point is gone. The comforting enormity of the dump truck version has been replaced by something that looks like no living animal. What the 2025 size study doesn't do is reattach the lamnid lineage. The finding updates the physical picture. It doesn't alter the taxonomy. These are independent corrections to independent errors, and presenting them as the same story would obscure both. One misconception runs through almost every popular account and deserves direct attention. Megalodon didn't evolve into the great white. The Otodontidae didn't become the lamnidae. These aren't semantics. A lineage goes extinct when it ends without descendants. A lineage continues through speciation when descendant forms survive into subsequent geological periods. The Otodontidae ended in the Pliocene. Megalodon was its terminal species, the last expression of a lineage that had run for nearly 100 million years. No living shark carries any part of the otodontid blueprint forward. The branch closed. The great white's lamnid lineage was already running separately, on its own trajectory, for an extraordinarily long time before Megalodon disappeared. It didn't step into Megalodon's ecological role at extinction. It was already occupying its own niche, on its own terms, shaped by different evolutionary pressures. The lamnids survived the late Pliocene oceanographic transition, not by inheriting anything from the megatooth lineage, but because their smaller size made them less dependent on the particular prey base that Megalodon required. Their endothermy allowed them to pursue prey into colder waters, and their metabolic architecture suited an ocean that was becoming colder and less hospitable to very large, very expensive apex predators. Global cooling at the end of the Pliocene contracted the warm coastal seas that Megalodon apparently used as nursery habitat. The diversity of large baleen whales, Megalodon's primary prey, based on isotopic evidence showing it feeding at the highest trophic levels, declined significantly. Their distributions shifted toward polar regions outside the temperature ranges Megalodon preferred. The ocean that had sustained a 15 to 20 meter apex predator, requiring enormous caloric inputs from enormous prey, became, in the space of a few million years, a different ocean. The otodontid strategy stopped working. The lamnidae were already elsewhere, running a different calculation. Stand in front of a megalodon jaw reconstruction in any museum, the rebuilt frame of interlocking teeth, the opening wide enough to swallow a small car, the visitors posing for photographs between the root surfaces, and you're looking at the accumulated consequence of a taxonomic decision made from illustrations in a 19th century atlas. The animal inside that jaw was classified as a giant great white because its teeth looked, to a mid-century naturalist working without quantitative morphometrics, similar to great white teeth. That similarity was real. The conclusion drawn from it wasn't. The teeth of Megalodon, thick, finely serrated, carrying a prominent bourlette, sitting on a robust V-shaped root, are the teeth of an otodontid. The teeth of a great white, thinner, more coarsely serrated, minimal bourlette, more rectangular root structure, are the teeth of a lamnid. The Nyberg, Champaglio and Ray morphometric analysis of 2006 demonstrated the separation quantitatively. Distinct clusters in morphological space, with great white teeth grouping alongside Isurus hastalis rather than the megatooth lineage. The evidence was there to be measured. It required the right tools and the willingness to look critically at an assumption that had been functioning as a foundation for over a century. The Otodontidae as a family appeared in the early Cretaceous, around 100 million years ago, and ran as a lineage through nearly the entirety of the Cenozoic era. They weren't a failed experiment. For tens of millions of years, they were one of the most successful large predator lineages the ocean had ever produced. Megalodon, the terminal species, hunted whales and pinnipeds across every major ocean basin from the early Miocene to the early Pliocene, a span of roughly 20 million years. Its teeth have been found in marine deposits on every continent. Evidence from study sites in the Reverte quarries of northeastern Spain and multiple American formations suggests it used warm, shallow coastal areas as nursery grounds for juveniles. A 2026 paper documenting a megalodon tooth found in the deep sea of the South Atlantic, embedded in a ferromanganese crust at 664 to 667 meters depth on the Rio Grande Rise, extended its known range further into pelagic offshore environments. It was a transoceanic superpredator, not a giant great white. The distinction between those two descriptions isn't cosmetic. The Lamnidae, running on a parallel track throughout, were doing something different the whole time, and doing it successfully enough that 5 of their species are alive in today's ocean. Their endothermy and speed allowed them to pursue fast prey across a wider temperature range. Their smaller body size, relative to the megatooth lineage, made them less dependent on the particular oceanic conditions that Megalodon required. When the world changed at the end of the Pliocene, the lamnid strategy proved more adaptable. The great white didn't step into Megalodon's ecological vacancy. It was already there, on its own terms, before Megalodon was gone. The reclassification doesn't just update a genus name in a taxonomic database. It severs the conceptual link between the 2 most famous sharks in the history of the ocean, a link that shaped how both animals have been understood, reconstructed, and presented for nearly 180 years. Every museum exhibit that placed the great white beside a megalodon jaw as evidence of family resemblance. Every documentary that described today's apex predator as Megalodon's legacy. Every textbook illustration built from great white proportions and labeled with the name Carcharodon megalodon. All of it descended, in an unbroken institutional line, from a single genus assignment in Agassiz's 1843 text volume. And all of it was working from a misidentification. The science corrected itself, as science does. Bozenecker and colleagues, Shimada and colleagues, and the researchers who have consistently used Otodus megalodon within Otodontidae in their published work weren't making dramatic announcements. They were working with the evidence as it had accumulated, the morphometric studies, the systematic analysis placing Carcharodon and the megatooth lineage on separate branches of the lamniform tree, the growing consensus that the ancestor-descendant framing was a category error embedded in a genus name. The public record hasn't caught up. Walk into most museums today, and the label still describes the great white as Megalodon's closest living relative. Many documentaries haven't corrected their narration. The textbooks revise slowly. Museum reconstruction committees are expensive to convene. But the 2 animals have been separated, not by a decree, but by evidence, by the patient accumulation of tooth measurements and morphometric analyses and systematic arguments across decades of specialist research. The separation was always true. It took the right analytical tools to demonstrate clearly. Megalodon was the culmination of a lineage that began in the Cretaceous and ended in the Pliocene. The Otodontidae built their dominance on size, on being larger than anything else in the ocean and hunting prey that nothing else could approach. That strategy worked for nearly 100 million years. Then the ocean changed and the strategy stopped working and the lineage ended. No continuations, no descendants. The branch closed completely. The great white's lineage, meanwhile, built a different kind of dominance. Speed, warm muscles, metabolic efficiency, the ability to operate across a wide range of ocean temperatures, ancestry tracing back through the broad-toothed makos of the Miocene. That blueprint proved more flexible when the world changed. 5 living lamnid species remain in today's ocean. These were always 2 separate evolutionary experiments. One optimized for scale until the environment could no longer sustain it. The other optimized for speed and metabolic range on an entirely different set of biological terms and outlasted the alternative, not by inheriting anything from it, but by surviving the same conditions that made it impossible. For nearly 180 years, the false taxonomy of 1843 bound these 2 separate stories together into one narrative, ancient blueprint and modern copy. ancestor and heir. The narrative was compelling. It was visually legible. It spread through every institution that tried to explain what Megalodon was and why the great white still swims in its shadow. The narrative was wrong. Megalodon belongs to the Otodontidae. The great white belongs to the Lamnidae. Their common ancestor lies somewhere deep in the early evolutionary history of mackerel sharks, far enough back that neither animal offers a meaningful biological window into the other's form, behavior, or survival. The most famous extinct predator and the most famous living predator were never running the same story. They were always running their own, in parallel, through the same oceans, on different biological terms, with different fates. If you want more cases where the science has moved and the public account hasn't caught up yet, subscribe.